In this paper, the authors introduce MC-JEPA, a new approach that combines two commonly used methods in visual recognition: self-supervised learning for understanding content in images or videos, and optical flow estimation, which captures how objects move. Traditionally, these methods operated separately, focusing solely on either object identification or motion analysis. MC-JEPA utilizes a shared encoder to learn both content features and motion information simultaneously. This unified approach enhances the understanding of visual data by integrating motion dynamics with object recognition. The authors demonstrate that their method performs competitively on standard benchmarks in both optical flow and various tasks like image segmentation. Overall, MC-JEPA represents a significant step towards more comprehensive self-supervised learning that can adapt to diverse visual challenges. Let's delve into the initial segment of the method section of an academic paper, which outlines the innovative techniques employed in optical flow estimation for video analysis. MC-JEPA architecture. The method described revolves around the architecture labeled MC-JEPA, which integrates motion learning through optical flow estimation derived from videos and content learning through a joint embedding approach of image views. This is achieved using a shared encoder that efficiently processes information from the different tasks simultaneously. The core of the optical flow estimation system is built on PWCnet, a prior model recognized for its capabilities in flow estimation. The process begins with a pair of consecutive frames, referred to as the frame at time t and the following frame, from the video. An encoder extracts a set of features at multiple resolutions from both frames, resulting in feature sets that represent both frames at different abstraction levels. The flow estimation is designed to progress from a coarse to a fine resolution. Initially, the algorithm estimates a basic flow vector using the lowest resolution features. The flow is represented as a mapping that aligns pixels from the first frame to corresponding pixels in the second frame. Once the initial flow is established, it is used to adjust the features from the second frame, which are then compared against the warped features derived from the first frame using a regression loss function. This comparison ensures alignment accuracy and therefore reliability in motion capture. The algorithm further enhances the flow estimation at each layer by iteratively predicting and refining the flow residuals. This adds corrections to the previous flow estimates progressively. The ultimate goal is to produce an accurate flow estimate that, when applied to warp the first frame, closely resembles the second frame. A reconstruction loss function evaluates this accuracy, strengthening the learning objective. To ensure consistency across the calculated flows at different resolutions, a technique known as cycle consistency loss is incorporated. This method minimizes the discrepancies between the features at every resolution layer, promoting strong correspondences throughout the network. However, a challenge arises during the training phase. The encoder experiences instability when tasked with multitask learning. To counter this, a variance-covariance regularization term is applied to each feature layer, stabilizing the training process and ensuring that the model converges effectively. Related work. The subsequent part shifts focus to the body of related research under the self-supervised learning paradigm, which has made significant strides in recent years. The narrative asserts that these advances have been largely fueled by techniques designed to learn invariances through various data augmentation strategies, utilizing joint embedding architectures. Different self-supervised methods are discussed, including contrastive and clustering techniques that influence how concepts are grouped in the embedding space based on their visual proximity. The landscape of self-supervised learning in images has drawn parallels to video analysis tasks, pushing for representation learning that generalizes well across action recognition benchmarks. Overall, this segment introduces the foundational aspects of the MC-JEPA architecture and situates it within the broader context of self-supervised learning and optical flow estimation methodologies, laying the groundwork for the experimental approaches that will follow. Continuing with the method section, the second part delves into the technical mechanisms behind optical flow estimation and self-supervised learning strategies utilized within the model. At the core of this approach is the regression and smoothness strategy. The authors modify the PWCnet flow estimator to integrate with a custom encoder architecture. The process begins by extracting features from a pair of images, denoted as X at different pyramid levels, before estimating the initial flow between the images. This is denoted as F, which acts as a mapping from one image to the next. The model then refines this estimate iteratively at progressively higher image resolutions, capturing finer details in the motion. Next, the flow estimator incorporates a calculation of a 4D correlation volume from the warped features. Essentially, this involves measuring the similarities between warped features of one image and features from another, facilitating more accurate flow estimations. A multi-scale loss approach is employed to ensure accuracy across various feature layers, using different forms of loss calculations to assess discrepancies between the predicted and actual features and images. The authors also introduce a cycle consistency mechanism, which addresses the inherent asymmetry in flow estimation. By computing flows in both directions, from I_t to I_t plus 1 and vice versa, the model enforces that warping features from one image through this dual process returns to the original image. This consistency helps enhance the accuracy of the flow estimation, especially in handling occlusions. Additionally, variance-covariance regularization is applied to stabilize the features generated by the encoder. This involves monitoring the variance and covariance of the feature representations, encouraging a healthier distribution of data that improves training dynamics. Transitioning into multitask self-supervised learning, the authors explain their strategy to jointly train on both optical flow and content features obtained through self-supervised learning. In this process, data augmentation techniques like random cropping and color jittering are employed to generate two views of the same image. The VI_reg loss function is then utilized to bring these views closer together in the feature space, aiding the encoder in learning robust, invariant representations. Finally, during training, the model alternates between updating flow estimates and optimizing self-supervised learning on image datasets. This concurrent training is executed through a combined loss function integrating all the aforementioned loss components: regression, reconstruction, smoothness, cycle consistency, variance-covariance, and self-supervised losses. This robust method sets up a strong foundation for the upcoming experiment section, where the authors will present empirical results demonstrating the effectiveness of their approach across various benchmarks. In the experiment section, the authors provide a comprehensive analysis of their model's performance across various tasks, primarily in optical flow estimation and instance segmentation. In the dataset subsection, they describe the datasets used for pre-training and evaluation, including well-known collections like Kitty and MPI-Sintel, alongside others such as Flying Chairs and Davis, 2017. These datasets yield a robust framework for assessing the proposed model's capabilities across different tasks. The main results subsection highlights the comparative performance of the model, MC-JEPA, against state-of-the-art methods in optical flow. Results presented in Table 1 reveal that MC-JEPA achieves results on par with top competitors optimized for flow estimation while providing improved outcomes compared to MC-RW, which shares similar objectives. This establishes MC-JEPA's efficiency in flow estimation as a precursor to learning more generalized features. Next, the authors delve into instance segmentation, where their model surpasses existing benchmarks like MoCo v3 and VI_reg, indicating that integrating flow estimation as a pretext task significantly enhances feature localization. Table 1 effectively summarizes these performance metrics across different datasets, illustrating MC-JEPA's competitive edge while transitioning into tasks reliant on both motion and content. In ablations, they analyze various configurations of the model, detailing the influence of dataset variations, Table 2, and architectural choices, Table 3. The results show that flow estimation performance improves when incorporating multiple datasets, with Kitty and Sintel yielding commendable results. Moreover, normalization strategies were crucial. Using layer norm helped stabilize the training process. This section further evaluates the backbone architecture and data sampling strategies, revealing that the CONVNXTT backbone proves more effective than ResNet, 50, or PWCNet. Particularly, data sampling methods indicated that alternating training batches yielded superior performance, as captured in Table 5. Finally, they present several ablation studies using visual figures, examining the optimal timing for starting flow estimation relative to ImageNet training epochs and the impact of cycle consistency and multitask balancing coefficients. These studies underscore the necessity of fine-tuning to maximize performance across tasks, emphasizing the trade-offs inherent in simultaneously learning motion and content features. As this section transitions into the conclusion, the authors have set a solid foundation for understanding their contributions and the significance of their findings. Conclusions. In this study, we introduced MC-JEPA, a novel multitask framework for self-supervised learning, focusing on motion and content features through optical flow estimation. Our findings demonstrate that MC-JEPA excels across various applications, including optical flow estimation and image and video segmentation tasks. This promising performance encourages the integration of multitask learning in self-supervised settings, potentially paving the way for feature learning that is adaptable to multiple downstream applications. Looking ahead, we aim to enhance our approach by leveraging larger datasets of natural videos to better capture both short and long-range interactions hierarchically. Ultimately, our work not only contributes a robust methodology, but also sets the stage for future explorations in self-supervised learning, enhancing understanding of video data processing and representation. Through these insights, we anticipate that MC-JEPA will foster further innovations in the field.